Okay, so we'll talk about rank of a matrix. So, as you know, matrix is a rectangular arrangement of the elements. So, suppose we consider a m by n matrix, A to 1, this is the second row, A to n, A m 1, this is the mth row, A m n. So, this is an m by n matrix. So, where ai's are coming from a field, here we are taking a real number, but it could be any field. So, now these elements are, so this is a rectangular of size m into n, and the entities are the elements coming from a field. So, here we are taking an example of real field. So, this is a real matrix. So, what is the rank of a matrix? So, rank of a matrix is, so if you take a matrix and we know the minor. So, it is the minor of say rank of A is R, means implies that we have a minor of size R which is not equal to 0, at least one minor. We need to get at least one minor of size R, not necessarily principal minor, any minor. So, it could be here also. So, minor means we take a submatrix of it and take the determinant of that, and that value should be not equal to 0. So, we should have a minor, at least one minor of order R which is non-zero, and every minors of order greater than R is equal to 0. So, this is two conditions. So, we take a we need to have a minor of order R, at least one minor which is non-zero, and all the other minors of order more than R, that means R plus 1 minor. If you take a minor of R plus 1, that will be 0, R plus 2 minor will be 0, R plus 3 minor will be 0. So, that is the definition of the rank. This is called determinant rank, definition of determinant rank. We will talk about the row rank, column rank, but this is the rank of a matrix. This is the definition. So, what is the definition of a rank of a matrix? So, let us just definition of rank of a matrix. So, it is a R. So, let R. So, this is a rank of a matrix A which is of size say m cross n. So, rank we say the rank of the matrix A, rank of the matrix A is R if and only if there are two conditions. So, we should have at least one minor of order R which is non-zero, at least one minor of order R, at least one non-zero minor of order R. So, that means we should have a submatrix of this matrix, and we take the determinant of that, and size of that matrix is R cross R, that one of such minor should exist. So, this is a submatrix A I 1, A I R. So, A J, so I plus I my, so A I plus, so it could be anything like J 1, J 2 like this, A J R, but the size of this is R cross R. And the second one is all the other minor of order more than R should be 0. Every minor of order more than R, that means R plus 1, R plus 2, r equal to 0. This is for every minor of order more than r. So, that means all the minor of order r plus 1 equal to 0, all the minor of order r plus 2 is equal to 0, like this, so on. Okay. So, this is the definition, this is called determinant definition of a rank. So, now we will take an example to see how to get the rank of a matrix. So, if you take a matrix like this, suppose 2, 3, these are real matrix, that means the elements are coming from the real field, but it could be general field also, but in that case we need to define the determinant over that field. Okay. But we know the determinant over the real field 3 0 4 2 6 9 minus 3 3. So, suppose we have given this matrix, what is the size of this matrix, how many rows? 3 rows and 4 columns. So, this is a 3 by 4 matrix. So, definitely rank will be, so rank of a matrix, rank of A is always less than equal to minimum of m comma n, if it is a m by n matrix, because that is the, we need to take a sub matrix whose minor is not equal to 0. So, we cannot have a sub matrix of size more than m or more than n, because that has to be a square matrix. The sub matrix has to be a square matrix. So, if we have a m number of rows, n number of columns, if m is less than n, say, so we cannot construct a square matrix of more than m. So, that is the condition. So, the rank has to be less than 3. So, rank is either 3, 2, 1, 0. 0, the rank of the 0 matrix is, so this is the convention, rank of 0 matrix is equal to 0. This is the convention. That means, if we have all the zeros entries, all are zeros. So, the rank of this is 0, because there is no such minor exist which can give us non-zero value. So, that is the convention, we take the rank to be 0. Okay, fine. So, now we want to get the rank of this matrix. So, how to get the rank of this matrix? So, we have to consider all the minors. So, what is the maximum minor we can have? So, 3 by 3, this is a, so we can consider this minor. So, what is the value of this minor? 3 0 4 6 9 minus 3. So, it is 2 into this, 2 into this. So, it is minus 3 and then minus of, just calculate the determinant, minus of this into these two. So, minus 9 minus 24. So, this is 3 into minus 9 is minus 24, then minus 1 into, so minus 1 into this into this. So, 27 minus 0. So, if we calculate this, we will get 0 over here. So, not only this, if you take this minor, you can find this is also 0. If you take this minor, like if you take 2, 3, 6 and then minus 1, 4, minus 3, then 1, 2, 3, you will see this is 0. So, all the, if you just to find out, all the minor of order 3s are coming to be 0. So, rank cannot be 3. Now, we have to check whether rank could be 2 or not. So, for that we need to find at least one minor of order 2 which is non-zero. So, let us try to get that. So, all the minor, so all the minor of order 3 is 0. So, this we have checked. I mean, we have checked 2, but you can work out for others minors of order 3 cos 3. So, that means rank must be less than 3. So, rank is either 2 or 1. So, now we have to check whether rank is 2 or not. So, now we have to consider all the minors of order 2. So, let us check that whether we can have a minor of. So, we just take this minor of order 2. What is the value of this? Yeah, so this is minus 9. So, this is not equal to 0. So, we got a minor of order 2 which is non-zero. So, that means from here we can say rank of A is 2. Okay. So, that is the definition of the rank. Rank of a matrix is just the index R such that we should have a minor, at least one minor of order R which is non-zero, and all the other minor which is more than R, that is R plus 1, R plus 2, those will be the 0. Okay. So, now this is the definition of the rank. Now, we say if we have a square matrix means the number of rows and number of columns are same. Square matrix. So, if you have a square matrix, say n cross n, suppose number of rows, number of column are same. Now, the rank would be n here, because this is square matrix. So, if the rank of this is n, this means the determinant of A is non-zero. So, then this is called a non-singular matrix. Then this implies, this is the definition, A is a non-singular matrix, where determinant is non-singular. Otherwise, if rank is less than n, then we say this is a singular matrix. Now, if we have a rank less than, if we have a singular non-singular matrix, then we know that it has a inverse. So, what is the inverse of this matrix? So, suppose A is a non-singular matrix. So, the definition of inverse is A into B should be the identity matrix. So, identity matrix means all are 0 other than this diagonal element, all are 0 element. This is n cross n. So, we should have a this, and the vice versa, we should multiply this in both sides, identity matrix, and then B is called inverse of A. Okay. Now, if A is a non-singular matrix, then inverse exists, and then we know the result, A into adjoint of A is equal to identity. A into adjoint of A is equal to identity matrix. So, this result we can follow, and we can get the that rank of a we can get the that inverse of a matrix. So, this is the result is telling no, this is not the result is telling A into adjoint of A, which is other way also, adjoint of A into A, this is telling us determinant of A into the, this is determinant of A into identity matrix. This is a result we can prove. Adjoint of A means we take each element and we replace by its cofactor. So, that is the, we will come to an example, that is the definition of adjoint. So, now if A is non-singular, then the determinant is non-zero. Then from this is the result, this one can prove it. Now, if A is non-singular, then determinant is non-zero, then we can do this thing, we can divide this by determinant. So, A into adjoint of A by date of A is equal to identity, which is from both sides, adjoint of A by date of A into A. So, this is our B. So, this is the inverse of A from definition. So, this is the A inverse. So, A inverse is nothing but adjoint of A, this is a matrix by determinant of A, while A is a non-singular matrix, while determinant of A is not equal to 0. So, that means if A is a non-singular matrix, then only inverse exists, and the inverse is of this form this. Okay, now, how to calculate it? We can just have a quick example. So, we can take a 3 by 3 matrix. So, just a quick example. So, suppose we have to take a non-singular matrix. So, 1 0 3 4 5 2 3 4. Now, suppose this is our matrix. Now, we have to check what is the determinant value of this. So, determinant of this is 3, which is not equal. You can easily work out on this. Now, how to get the adjoint of A? Adjoint of A means we just this one we are going to replace by the cofactor this. So, this is basically nothing but determinant 4 5 3 4 this place. Then minus of this will be replaced by this minus means minus symbol. So, this is 3 5 2 4 the determinant, this is the cofactor. Then we have for this we have 3 4 2 3, and this is also a 3 by 3 matrix, and this one is replaced by. So, we ignore this row and this column. So, this determinant 0 1 3 4. Okay. So, like this. So, 0 1 3 4. So, this is the way or transpose of it. So, anyway, so this is if we calculate it, finally, I am not going for details of this calculation. So, finally, we will get the matrix like this 1 3 minus 4 minus 2 2 minus 2 1 minus 3 4. Okay. Details calculation will be given in the note, but this is the calculation. So, and determinant of this is 3. So, what is the inverse of this? Inverse of this is adjoint A by det A. So, 1 by 3 into this matrix. So, you can just take this 1 by 3 inside. So, it is 1 by 3 1 minus 4 by 3, then minus 2 by 3 2 by 3 2 by 3, then again 1 by 3 minus 1 and 4 by 3. So, this is the inverse of the corresponding matrix this. So, since the matrix is non-singular, then only inverse will exist. Okay. So, this is the inverse. Now, we will see later on how you can get the, because the finding adjoint is very difficult for the large matrix. So, how we can get the inverse for a large matrix? So, we have to do the some kind of elementary operation, row operation, column operation. So, we will see that. Okay. So, let us just talk about how to find the elementary operations to find the rank of a matrix. So, the question is, suppose you have given a matrix any order, it could be m by n, and these elements are coming from the real field set. Again I am telling it could be general field. Okay. So, now the question is how to find the rank of A. Now, one way to get the rank of A is to, we have seen that we can check the all possible minors, and then we start with the minimum of this, then we start checking all possible minors, and once we get a non-zero minors of some order, then that will be the rank of the matrix, but that is difficult for a large matrix. Okay. So, what is the solution? Solution is the elementary operation. Elementary operation. This is either row operation or column operation. So, there are three types of elementary operations. Suppose we are talking about row operations on row, and same thing will be carried out for column also. So, row operation. So, we have a row like we have a matrix A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. So, this is referred as row number 1, first row, this is referred as second row like this. So, this is referred as mth row. There are m row and n columns. So, this is the first column, second column like this. So, in general we have a jth row, ith row. Ith row is here ai1, ai2 dot 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 ain. So, this is in general this is the rj, ith row. Now, row operation, elementary row operation means we can do the three types of operation. One is we can exchange two rows, say we can exchange first row with second row or ith row with jth row. So, that is denoted by we can exchange the row. This is one operation. This is referred as rij. We are exchanging the row. If we exchange the first row, second row, first row will come here, second row will go there. So, that is referred as R12. So, we are exchanging the rows. First row is coming to the second row is coming to the first row. So, in general this is Rij. So, that means rth row is going to the jth row and jth row is going to the rth row. So, this is one operation. So, this is exchange of row, exchange of two rows. This is only on two rows. And similarly, we can do for column also, exchange two column. So, we have Cij. This means Ci and Cj. So, jth column and ith column both are getting exchanged. So, this is the on column operation. Okay. Another operation is we can add some constant on any of this row or for column any of the. So, this is the second elementary operation is Ri. We consider the ith row, Ri we replace by some constant into Ri. Say some constant, say lambda or some alpha into Ri. So, this is referred as we multiply some constant with the ith row. So, if the ith row is, if Ri is this, Ri is R A1, I2, In. So, this will be replaced by, we have to multiply a constant alpha ai1, then alpha ai2, alpha is another real number Ain. So, this is referred as, so this will be replaced by alpha times all these elements. So, this operation is referred as Ri multiplying a scalar or the constant real number. Here we are talking about real field. So, multiplying a scalar on the each element of the row, that is referred as this. Okay, this is one operation. Similarly, for column we can have Cj is going to some alpha times Cj. We can take a particular column, jth column, then we can apply constant on this. So, that is the one column is going to replace by the constant time of that column. So, this is the another elementary operation. And the last elementary operation is last elementary operation is we can take a row this is replaced by, we can just do like this. So, that means we can, so we have a row, say ith row and jth row. So, this is this is r I 1, r I 2, r I n, sorry, a I 1, a I 2, a I n, a j 1, a j 2, a j n. Now, this is our ith row and this is our jth row. So, under this operation what we are doing? We are multiplying this by alpha and then this row we are replacing by this row, we are replacing only r I. So, r I is replacing by r I 2, r I n, this is replacing by, we are multiplying alpha with this and then we are adding with this. So, r a I 1 plus alpha times a j 1 comma a I 2 plus alpha times a j 2 and so on, a I n plus alpha times a j n. So, this is the way we are continuing. So, this row is going to replace by this row plus some scalar multiplication of the other row. So, we will do this type of. So, this is the another operations and similarly we can do it for column also. So, the ith column can be replaced as C I plus alpha times C j. Similarly, we can do the same operation on the column. So, this will be elementary column operation. Okay. So, we will continue with this in the next module. So, so we will see how this elementary operation can be can help us to find the rank of a matrix. Okay. So, we will talk about in the next class. Thank you.